In this video, we go over the kernel and range of a linear transformation. We'll see that the kernel and range of a linear transformation are subspaces of the domain. So the kernel is a subspace of the domain, and the range is a subspace of the codomain. And the two of them help us to understand the particular linear transformation we're looking at. Okay, so first let's go over the kernel. Basically, the kernel of a linear transformation is all the vectors in the domain that get transformed into the zero vector by t, and we denote the kernel by ker of t. Okay, so for a linear transformation, the zero vector in the domain always gets transformed into the zero vector. From the definition of the kernel, it should always at least contain the zero vector, but it may also contain other vectors, right? So basically the kernel is the preimage of the zero vector. Okay, so let's look at a few examples where we try to find the kernel. So the first example here is the identity transformation, because basically the identity transformation keeps every vector the same. So if we want to find the kernel, right, so it's everything that gets transformed from the zero vector to the zero vector, right? So we need to solve, so find v such that v gets transformed to the zero vector. But transforming a vector for the identity transformation doesn't do anything, right? So this just means, so the transform of v just gives you v, and so this says that v has to be the zero vector. So that's the only thing that gets transformed to the zero vector, and so the kernel here is just the zero vector. Okay, so what about the next example? So here we have a linear transformation that sends every vector to the zero vector, and so clearly here, if every vector is sent to the zero vector, that means that the kernel has to be everything in the domain. Okay, so then third example on this page, we have a transformation from the plane to itself, where it takes a point xy and it swaps the x and y coordinates, right? So the y coordinate becomes the x coordinate, the x coordinate becomes the y coordinate. And if you think about this geometrically, this transformation just gives the reflection about the line y equals x, right? Because if you have, say, some point x comma y, and you swap their coordinates, it just means that you're flipping it over the line y equals x. Okay, so if we want to find the kernel, we want to find xy such that it gets transformed into the zero vector, which is 0, 0. But then what is t of xy is just y, x. But then this says y is equal to 0 and x is equal to 0. So that means that, again, the kernel is just the 0 vector. Okay, so the examples on this page are fairly straightforward in trying to determine the kernel, but what happens in a more general case? Okay, so in this example, we look at a linear transformation that's given by a matrix A. So this matrix A here, and we want to find the kernel in this type of problem. Right, so as usual, finding the kernel means to find all vectors x such that T transforms x to the 0 vector. Okay, so in this particular example, transforming x just means multiplying by a. Right, so that means that we're looking at solving ax equals 0. But if you notice, solving ax equals 0 means trying to find the null space, right? So in the situation where the transformation is given by a matrix A, the kernel is exactly the same as the null space of the matrix. Okay, so basically this problem just boils down to figuring out what the null space of this matrix is, right? So we're just solving ax equals 0, right? So we can set up the augmented matrix. Because it just means we're solving this x1, x2 is equal to 0, 0. And then this is the augmented matrix 1, negative 1, 2, 0, 1, 2, 0, 0. And then if we put it into row reduced echelon form, this is not too difficult, right? Because we just need to add the second row to the first row. Okay, so x1. Oh, the domain is R3, right? So this should be, so be careful here, make sure everything has the correct dimension. Right, so the domain has to be R3, right? Because this is a 2 by 3, so this needs to be a 3 by 1, and then so the result is 2 by 1. Okay, so I have three variables, x1, x2, x3, right? So this is x1, this is x2, this is x3. So the leading coefficients are here and here. So that means that x3 is free. So that means that I can parameterize x3. And then what does row 1 say? Row 1 says that x1 plus 4t is equal to 0. And then row 2 says that x2 plus 2t is equal to 0. So that means x1 is equal to minus 4t, and then x2 is equal to minus 2t. Okay, so what do we get? x1, x2, x3 is equal to, x1 was this, which is minus 4t, x2 is minus 2t, and x3 is t. So the kernel of t is exactly this. Okay, so one thing to keep in mind, so again we see that here the kernel of t is the same as the null space, right? And this is true for any linear transformation that's given by a matrix. The kernel is the same as the null space, and because we know the null space is a subspace, that means the kernel is also a subspace, and it's a subspace of the domain. Right, so this is true in general. The kernel of any linear transformation is a subspace of the domain. So it's not hard to see why this is true, right? To prove it, we just need to prove the two conditions of our subspace. Right, so that's closure under vector addition and closure under scalar multiplication. So what does closure under vector addition means? It means you take two vectors in the domain and right, so but this is for the kernel. Right, so I take two elements in the kernel and then the sum should still be in the kernel. Right, so so for u and v in the kernel, so because they're the kernel, that means that they get transformed to 0. But then now, if I add plus u and v together, and transform them from the property of a linear transformation, I can write it like this, but then t of u is 0 and t of v is equal to 0. So this is just 0 plus 0, which is the 0 vector. So this shows that u plus v is also transformed to the 0 vector, but that means that u plus v is in the kernel. Right, so this shows that it's closed under vector addition. Okay, so now we verify the second condition. Right, so we take u in the kernel. What does it mean to be in the kernel? It means that it transforms to 0. But now what about the scalar multiple of u? If I transform that, then from the property of a linear transformation, I can write it like this, but then t of u is just 0, and then c times 0 is 0, right? So this shows that c times u also gets transformed to 0. So c times u is in the kernel. And so this shows that the kernel is also closed under scalar multiplication. Okay, so we have that the kernel is a subspace of the domain. Okay, so now we switch our attention to looking at the range. Right, so if you remember, the range is the set of all elements in the codomain. So it's basically all the outputs of the linear transformation as we take all possible inputs from the domain. Right, so this is a subset of the codomain. So similar to the kernel, the codomain, the range is also a subspace, and the range is a subspace of the codomain. So again, the two closure properties are not hard to see, right? So it basically follows from how linear transformations behave. And just like in the situation where the linear transformation is given by matrix multiplication with A, where the kernel is the same as the null space, we can see that the range is the same as the column space. Right, so why is that? Right, so if we write out the equation AX equals B and think of the columns of A as being separate column vectors, right, so say V1 through Vn, right, so here I've written the equation AX equals B, where A is separated by column vectors, and then X is just the vector with coordinates x1 through xn, right? So multiplying by A with this matrix here, and if I multiply it out, I get exactly this linear combination. And so this shows that the output vector B can be written as a linear combination of the column vectors of A, right? But then as you take all possible vectors X that runs through all vectors in Rn, right? You let x1 through xn vary, then you get all possible linear combinations of the column vectors. And so any output vector can be written as a linear combination of the column vectors, and so the range is the same as the column space. Right, so so this gives us a way to easily determine the range of a linear transformation whenever it's given by a matrix. Right, so it's just the same as the column space of the matrix. In general, for general functions, it's not so easy. It's not always so easy to figure out what the range of the function is. But in the case of linear transformations and vector spaces, because of this condition here, it's just the same as the column space, and we know how to calculate the column space. Okay, so in this example, we're taking the example from before, right? So the linear transformation given by this matrix A here, and now we're going to try to determine the range of T. Right, so from the previous discussion before, range of T is the same thing as the column space of A. And if we go back to chapter 4, one way to find the column space of A is to take the row space of A transpose. Right. So if you go, what section was that? That was section 4.6. Right. So in section 4.6, there were two methods of finding the column space. Right. So method one was that the column space of A is the same thing as the row space of A transpose, and then there was a second method. So in this example, we're gonna use method one, but it doesn't really matter. You can use either method. Okay, so we're gonna find the column space of A by looking at the row space of A transpose. Right, so what is A transpose? So this is the first column, right? So 1, -1, 2, and this becomes the second column, so 0, 1, 2. Okay, so then to figure out the row space, now I take the row reduced echelon form. So I've already calculated it previously. However, the calculator doesn't like it when you try to calculate the row reduced echelon form of a matrix with more rows than there are columns. Right, so I had to add an extra column of zeros, but you can just ignore this in the calculation, right? So this 3x2 matrix is the row reduced echelon form. Okay, so here the non-zero rows are the basis vectors. Right, so we get that the range of T is the span, first row is 1, 0, and then the second row is 0, 1. But this is just the standard basis of R2. Right, so the span of the standard basis gives you all of R2. Okay, so so in this example, the range is the same thing as the codomain. So let's see how the range and the kernel are related. Right, so if you remember again from chapter 4, there was something we can calculate involving the various dimensions called the rank and the nullity. Right, so this was from chapter 4 again. Right, so you have the rank of the matrix and the nullity of the matrix. Right, so the rank is related to the column space and the nullity is related to the null space. Right, but in the examples we're looking at, the range is related to the column space and the kernel is related to the null space. Right, so we can define the same concepts for linear transformation. Right, so the nullity is the dimension of the kernel and the rank is the dimension of the range. And then we have the same equation that relates the two from before, right? So the rank of T plus the nullity of T has to be equal to the dimension of the domain. So what's going on in this case, right? So the dimension of the domain is 3, right? Because it's R3. And then dimension, the rank, here dimension of the range is 2. So this means that the dimension of the kernel, so the nullity, has to be 3 minus 2, right? Because this n minus the rank is equal to the nullity. Right, so 3 minus 2 is equal to 1. So the dimension of the kernel is equal to 1. But this is the same example we did before for the kernel, right? So you can see here the kernel is clearly one-dimensional, right? Because as t varies, you form a line in three-dimensional space. There's one free variable, right? So what was that, example 4, right? So okay, so this agrees with what we calculated previously. Okay, so on this last page of this section, we discussed two more properties of linear transformation. So the first is called one-to-one, and the second is called onto. And we'll see that one-to-one is related to the kernel and onto is related to the range, right? So basically, a function is one-to-one if the preimage of every element in the codomain is exactly one element in the domain, right? So we've seen previously that sometimes the preimage can have multiple elements, but for a function to be one-to-one, this can't happen, right? So again, a function is one-to-one if the preimage of every element in the codomain is a single element in the domain. Okay, so that's what it means to be one-to-one, and onto means that the range is the same as the codomain. But in terms of linear, so the concept of one-to-one and onto apply for any function. And again, for general functions, sometimes it's not so easy to figure out if they're one-to-one or onto, but for a linear transformation, it's actually straightforward, right? So to see that a linear transformation is one-to-one, you have this condition here where it's one-to-one if and only if the kernel is just the zero vector. And then similarly for onto, if W is a finite, if the codomain is finite dimensional, then the linear transformation is onto exactly when the rank is the same as the dimension of the codomain, right? Because in that situation, they're exactly the same. So if we look back at the example from the linear transform examples 4 and 5, right? So in example 4, we see that the kernel is not just the zero vector, right? So that means it's not one-to-one. And in example 5, when we calculate the rank was 2. The dimension of the codomain was also 2. Right, so we just need to compare the dimensions. And so because they're the same, we can see that the linear transformation is onto. Right, so again, this condition here makes it easy to check if it's one-to-one or not. And this condition here makes it easy to check if it's onto or not.